Welcome to the Deep Dive, where we take complex source material and, well, we distill it down to the critical insights you really need to know. And today, we're looking at something fascinating: the foundational documents for a university-level software engineering course. You know, if you ask most people what coding is, they get this picture in their head. It's one person alone in a room just quietly solving a puzzle.
Right, the lone genius stereotype.
Exactly. But the material we're diving into today, it suggests that building software is, well, it's so much more. It's this huge organizational, philosophical, and even historical challenge.
That's the core of it. Our mission today is to unpack that foundational debate. Is software development really an engineering discipline? And, why did that very question cause what they called a crisis decades ago?
So we're tracing the history here.
We're going back to the software crisis of the 1970s, which really forced the industry to try and standardize. We'll look at how software engineering was first defined, the debate around it, and maybe most importantly, show you why success today takes so much more than just technical chops.
Okay, let's get into it. The source material here is guided by an expert who has spent decades in this field. And what's immediately clear is that, expertise rarely comes in a straight line.
It's a fantastic example of cross-pollination. The instructor's background actually starts in music education.
Music education, really?
Yeah. And that creative foundation apparently led right into computer science degrees and then a career spanning almost 40 years. We're talking over a decade at a giant like GE, then 15 years in consulting and 10 years teaching.
So this is experience that's seen it all: finance, manufacturing, healthcare systems, deep data architecture, security.
It's the definition of battle-tested. It's the wisdom you only get from watching massive real-world systems succeed and fail.
And it seems that deep historical view really informs the whole teaching philosophy. The source even mentions a personal hobby of building old computer kits, specifically something called the PDP-10.
Yes, and that's not just a fun little detail.
Wait, so why is the PDP-10 relevant here? I mean, it sounds like ancient history.
It is ancient history, and that's exactly why it matters. The PDP-10 was one of the main systems used to build the ARPANET.
The ARPANET, the precursor to the internet.
The direct precursor. So if you get your hands dirty with the machine that started it all, you understand the complexity we've inherited. It grounds all these abstract lessons in reality.
So what's the goal of that approach? What's the teaching philosophy?
It boils down to two things. First, build intuition, don't just memorize commands. And second, and this is maybe the most crucial part, teach people how to find useful documentation and standards.
The classic teach a person to fish idea.
Exactly. The goal is independence. You don't want to create someone who can only solve problems they've seen before. You want to create someone who can solve any problem they encounter.
That idea of teaching independence seems key. Let's shift to the main goal of this course, because it really sets the stakes for the whole field. It's about building large, reliable, enterprise-scale applications.
And this is where we hit that huge philosophical question that started everything. Is software development actually engineering? I mean, if you're building a bridge, you have physics, you have standardized practices. But with software...
It is Wild West.
For a while, yeah. And the term software engineering was basically coined in response to that chaos. We have two key definitions from that era that really framed the whole debate.
Okay, what's the first one?
The first is from F.L. Bauer back in 1972, and it's more aspirational. He said software engineering is the establishment and use of sound engineering principles to get software that's built economically, is reliable, and, actually works on real machines.
Sound principles. Okay, that seems reasonable. A good goal to aim for. But then there's a second definition.
A few years later, 1977, Jeffrey and Linden. They were much more assertive. They didn't say it should be engineering. They argued it already is engineering.
So just as legitimate as civil or chemical engineering.
Exactly. They said it had more in common with those disciplines than people realized. And that insistence, that push, it was really born out of fear.
Fear.
And frustration. It was driven by what was officially being called the software crisis of the 1970s. Management engineers, Everyone was sounding the alarm, systems were failing, projects were way over budget. The whole industry felt like it's spinning out of control.
And the source material points to 4 specific failures driving this crisis.
Right. First, costs were just soaring. Second, the complexity of what people wanted software to do was outpacing what engineers could actually build. Third, you had a huge shortage of properly trained programmers.
And the last one was about hardware.
Yes. Hardware was moving so fast, new chips, new architectures, that the software tools to manage it all just couldn't keep up.
The statistics from that time must have been pretty stark to call it a crisis.
Oh, they were. If you look at the data from B.W. Boehm in '77, he tracked something called the shifting system cost drivers. Before 1970, hardware, the physical machine, was, the most expensive part of any system.
That makes sense.
But right around the turn of the decade, the cost of the software just skyrocketed. It blew past the 50% mark and just kept climbing.
So if software is suddenly most of the cost, and it's also where all the failures are happening, the focus has to change. It's not about the machine anymore.
Precisely. The bottleneck wasn't a lack of computing power. The bottleneck was the human side of building things. And that's why the modern job of a software engineer is so much more than just programming.
Right. The source says coding is actually just a small fraction of the job.
A tiny fraction.
So what else is on that list? What defines the job today?
Well, it's broad. You have to understand the infrastructure, the cloud, the network, everything underneath. You have to connect what the business wants to do with the right automation. And crucially, you have to talk to everyone.
Talk to the business people. Talk to the tech people.
And translate between them. That's maybe the hardest part, separating the what from the how.
It sounds less like a programmer and more like a diplomat, a manager, and an architect all rolled into one.
That's a good way to put it. And there's this striking bit of math from that era that drives the point home. A formula from Jansen and Tony's in 1979.
A formula for what?
For effectiveness. It's simple, but it's powerful. It says E equals C times M times CS. Break that down for me.
E is your net effectiveness on a scale from 0 to 1.
Wait.
C is your communication skills. M is your awareness of management concepts. And CS is your computer science ability, also on that 0 to 1 scale.
Oh, wait, so it's a multiplicative formula, not additive.
Exactly, and that's the devastating insight.
So if I'm the most brilliant coder in the world, my CS is a perfect 1.0.
Wow.
But I'm terrible at communicating my ideas, so my C is, say, 0.1. Then your total effectiveness is capped at a tiny fraction of what it could be. A low score in communication or management awareness doesn't just hurt you a little bit, it multiplies your entire contribution down towards 0.
Wow. That completely changes how you think about skill. And it explains why they couldn't just copy what other engineers were doing.
It does. Think about the classical design process for, say, a bridge. You have problem formulation, analysis, a search for solutions. You decide, you create a specification, then you implement.
It's very linear, very structured.
And it works great when the physics of steel and concrete don't change halfway through the project. But when they try to apply that same rigid process to software in the 70s and 80s, it failed consistently.
Why? What was the failure point?
Schedules slipped, quality was all over the place, but the real killer was that the requirements were always changing. Software is different, it's invisible and it's volatile.
Invisible, meaning a manager can't just look at it and see that it's 75% done.
Right. And volatile because the moment you show a user the first version, they immediately realize what they really wanted is something completely different.
And that breaks the whole classical model. You can't just freeze the requirements like you can with a blueprint for a house.
Exactly. The business side loved the idea of a formal process because it seemed to promise reliable budgets and schedules. But software it refused to cooperate. Applying that old world rigor without accounting for change was a recipe for disaster.
Which brings us right back to that central unresolved question you have to confront. Is software engineering actually engineering? Or is there this element of art or craft that you can't formalize?
And how do new tools like AI and LLMs change that debate today? Are we getting closer to a real standardized engineering or maybe even further away?
The source material suggests there's no single right answer to that.
No, it suggests the answer is something a team has to decide for itself. The course goal is to explore this stuff for a few weeks and then, most importantly, apply it. And the core concept is the difference between agreement and consensus.
That's a great distinction. Consensus is where everyone believes the exact same thing.
Which almost never happens on a complex project. Agreement is different. Agreement means the team commits to one path forward so you can actually start building, even if one person had to make the final call.
It's about unified action, not unified thought.
Precisely. And to help guide that action, the course points to 2 essential books, not textbooks, but field guides based on decades of real-world observation.
And these are the critical takeaways for anyone listening. What are they?
First, the absolute classic, The Mythical Man Month by Frederick P. Brooks, Jr.
The one that says adding more people to a late software project just makes it later.
That's the one. It explains why that happens. The initial readings point to 2 chapters. Chapter 2, The Mythical Man Month, and Chapter 14, Hatching a Catastrophe. They're all about misjudging complexity and the cost of communication.
Okay, that's book 1. What's the second?
The second is The Pragmatic Programmer. And together, the wisdom from these two short, really practical books is what gets debated and then applied.
And that application part is where the theory stops and the work begins.
Right. The students form teams, they get an architecture for a multi-tier application, and by week 6, the debate is over. They have to commit to their tools, their techniques, and start building. You read, you debate, you agree, and then you build. That's how you turn these historical lessons into something useful today.
Which brings us all the way back to that effectiveness formula. E equals CMCS. Communication times management awareness times technical skill. So let's leave our listener with this. If you look at how we build enterprise software today, with distributed teams all over the world, complex cloud systems, and business needs that change weekly, which one of those 3 variables is the most likely bottleneck on a project in 2026?
Well, you could argue technical skill CS is higher than it's ever been. And management concepts, M, are pretty widely taught in business schools.
Which leaves C, communication.
It's always the most vulnerable point. It's the human element.
Because it's the one thing that, if it fails, can bring that whole equation crashing down to almost 0. So here's the provocation for you. If you want to exponentially boost your own effectiveness, is your next step to get even better at the technical skills you already have? Or is it to master the art of clear, persuasive communication with everyone on your project?
Understanding the deep history of why we do things this way, that's the first step to real mastery. Start with the foundations. Start with the Mythical Man Month. That deep dive is always there waiting for you.